All right. So thank you all for coming, and thank you to Armando, Susan, the Ravenpack team for having me here. It's a great forum. The content, the speakers, they get better every year. So thank you all for coming. All right. So I'm going to start by talking about opportunities for machine learning within equities trading. So I belong to the equities trading business at RBC. That is what we deal with every day. So equity markets, we generate about 100 gigabytes of market data every day. We are processing billions of messages, whether they're trades, quotes, cancellations, additions to the order book, all sorts of stuff. So the main message is, if you have so much data available, we hope that we can use machine learning to solve some of the challenges that we face within this business. So when we talk about applying machine learning, I believe if we focus, if we have some guardrails around what could be the opportunities, our chances of success will be much higher. So if we focus on applications that deal with rational human behavior, we heard about it earlier in the panel. If there's some economic intuition, I believe the chances of success are higher. That's mainly because human behavior is somewhat more predictable. It's very hard to change people's habits. It adds stationarity to the processes, and you can easily interpret it. And from a regulatory point of view, you are easily able to explain human decisions which are based on human behavior. A few other things, we should aim to augment and not replace currently what we are doing. So that kind of addresses concerns around AI taking over the world and putting everyone out of work. That's not the goal here. So that way all the stakeholders can work together and address all the regulatory and competitive challenges which this industry faces. So if you look at opportunities to apply machine learning, I'm going to focus on things which are not price prediction or return prediction, because that's been extensively covered today. So we have transaction cost analysis that I'm going to talk about today. Then in the sell side, we talk about algo recommendation engines. The idea here is when an order comes to you, how do you decide how to trade it? What algorithm to use? We have a similar problem on the buy side. There's something called algo wheels. The idea is, you automatically decide, which brokers, which algorithm to use, when an order comes to the desk. It's all automated. Then there are applications around optimal trading, portfolio execution, hedging. In fact, there's a very interesting paper by Marcos Lopez de Prado. He talks about, many other applications within finance. All right. So coming to my problem of interest here, we are essentially talking about trading algorithms, how to attribute performance. This is a problem that we deal with every day in our business. The idea is how to get better executions for our clients. How to improve performance for them. How to increase engagement with them. So when we talk about order performance, we essentially have three classes of factors. Extraneous factors, which are somewhat client-determined or not under our control, like if there's some alpha in the trades, or how the market was behaving that time, vol regime and stuff like that. Then we have algo and stock parameters. These are under our control or known a priori. So you have algos like dark algos. So how much should I expose to dark pools when I trade? Or what kind of percentage of volume should I target when I trade? Stock parameters, which are known a priori, are spreads, daily volumes, vol of the stock. And the third class is algo behavior. This is essentially a response, how the algo behaved based on the first two classes. So how much was the actual percentage of volume realized? How much did we actually execute in the dark based on our instructions? So as you can see, we have all these features which we believe affect performance. The challenge for us is to understand, what are the important features, how they interact with each other, how are they related to the response variable of interest, which is performance, and how we can understand and how we can use that information to improve performance. So I hope you agree with me that this is a pretty classic machine learning problem, which we hope to solve here. All right. Let's see how we actually do this in in real life. The first step is to identify all possible parameters that we believe would affect algorithm performance. So these could range. This could be in hundreds or even thousands. Once we have that, we take our order executions. When I say order executions, we look at everything what that happened when the order was trading, what price it got filled at, where it got filled, what time it got filled, all sorts of metadata. Beyond that, we also record what was happening in the markets at that time and also some macro variables. Then the next step is to construct all these features. So this is like a typical data science step. You do pre-processing, feature engineering, normalization, all sorts of stuff. So once you have all of that, you build your normalized data store, which is you have your response variables, and you have all these features which you believe affect performance. And then we apply our performance attribution, the machine learning process, and we hope that the insights that come out, are more, are deeper and more actionable than what we have seen so far. All right. So quick review of the underlying methodology. We're using random forests here. We could have as well used gradient boosting or quite a few similar techniques. The main idea here is it's an ensemble learning method. You're constructing many different models, and you combine them together, and the final model is essentially an ensemble average of all of that. And that helps with handling nonlinear interactions, categorical variables, multicollinearities, all sorts of stuff. And to be honest, with so much democratization of machine learning techniques, these things are fairly straightforward now. The two key outputs we are interested in are variable importance and partial dependence. By variable importance, I mean it's essentially a ranking of which feature is more important, or which feature is explaining the most variability in the process. The nice thing about random forest, this output comes out pretty naturally. So you get a ranking of the important variables which are affecting performance, and on the x-axis here you have the amount of variance being explained. The next output of interest is partial dependence. So once we have our important variables, the next step is to understand the relation between those and the response variable of interest. So let's say I think stock return is very important, right? So I can easily see the relation between performance and that. And usually these relations are very nonlinear. So I have a simple example of a cancer prediction model, and you can see, you can see on the first chart, the relation between age and my response variable is very nonlinear. And if you use linear regression or univariate correlations, these things will not be very apparent. So that's why we have realized good value from random forests. All right. So I think let me go into the case studies now. So just to summarize, what we did here is, we came up with like hundreds of these candidate features which we believe affect performance, and then we are trying to, run performance attribution with random forests. The performance variables of interest are, usually slippage or arrival cost or something along those lines. So in this case study, we are looking at, a client who uses liquidity-seeking algorithms to trade with us. Usually these are used by clients when they are willing to work the order, but also looking to opportunistically source liquidity as they trade. And we have like thousands of orders in this sample. So this is the chart here is sorry. That's the variable importance plot, which I was mentioning earlier. So as you can see, the most important variable is stock return. Stock return is essentially how much the stock moved as we were trading. The other important variables are opportunistic liquidity wave fills, then minimum percentage of volume wave fills. I'm going to go over all of this in the next slide. All right. So the first inference was, there's an outsized dependence on stock return. And further analysis kind of told us, that indicates a lot of alpha in the client's trades. So the orders are, the trades are very directional. Like the client is trading when they believe it's the right time for them to trade. And that's why the stock return is like the most important variable. Then I also looked at partial dependence. So the first two plots on the left side show the partial dependence of two other important variables versus the performance. First is opportunistic liquidity wave fills. So what you notice here is, this is how a liquidity-seeking algorithm usually operates. The more liquidity you take, usually you should see less arrival costs or less slippage because you are trying to get more liquidity at better prices, and that usually helps. The next chart is min POV wave fills, this one. Essentially dealing with, so what are min POV wave fills? Min POV wave fills are, when typically a client trades, they will say, I want to always participate with some minimum participation rate. If I don't, end up with that rate, my algorithm will go and start taking liquidity so that I come back to that participation rate. And as you can see, it's pretty, it's probably the most inopportune moment to take liquidity because you're not really using any, you're being very irrational in when you take liquidity, and that, leads to worse performance. The chart on the right is the 2D partial plot. This is showing the effect of stock return, that is how much the stock moved, as well as opportunistic liquidity wave fills together on the slippage. So the key observation here is, if you go from left to right, generally the performance gets better, and that is, no matter if the stock is going against you or not, liquidity wave fills are pretty beneficial. So the next steps here would be from, if you want to further look at how to improve performance, would be what can I do to reduce my min POV wave fills. So one thing you can do is reduce your thresholds for understanding what is opportunistic liquidity. So then you're going to take more liquidity via those waves, and automatically you would see less liquidity being grabbed via min POV waves. All right, I have 6 more minutes, so let me go over the second case study very quickly. This is another kind of smart algorithm which our clients use. It's called smart market orders. The one key observation here was, if you look at the variable importance plots, the second most important variable is amends. So this is a client who's it's a discretionary trading desk. So while they trade, they amend orders a lot, and we saw this, and then we looked at, the partial dependence of these amends. That's the plot on the top right. And you can see as you amend the order more, you're actually paying costs. So essentially, this is like kind of human behavior, kind of getting impatient with the algorithm. You tweak some of the numbers, you replace the orders, and it might lead to worse performance, and we see that. All right, so I'm getting close to the end. To conclude, this is a case study of applying machine learning to transaction cost analysis. We were able to unlock a lot of different complex interactions, trader amends, opportunistic liquidity fills, and these are a lot more important, in dealing with algorithm performance versus, more legacy parameters like spread and ADV of the stock. So you can run it in very highly scalable fashion. And just to end, I just want to say that you should expect a lot more developments in this space as ML, machine learning gets more popular and democratized, and as other speakers have said before, these techniques usually are great, but we should keep in mind that financial data is very noisy. Domain knowledge is always going to be important in dealing with outliers and edge cases. Thank you.
Okay, so do you have any questions? I think we have one on Slido. Susan?
Yeah, how do you identify impact versus client alpha?
So that's a very good question. I'm happy that someone asked that. It's not easy, and it needs further analysis. So typically, what can happen is if the participation rate is low and you see a huge dependence, that might be a signal. You can also look at how the stock price moved after you traded the order. That might be another way to look at it. But there's many other ways. I just mentioned 2 of them.
Can we have one more on Slido?
Yeah, absolutely. How do you identify impact versus client alpha?
Sorry, we covered that.
I'm so sorry. How do you decompose post-trade market impact and identify your own impact?
Again, that's a very good question. There are many ways to do it. You look at reversion. You look at how the stock moved after you traded, over different time periods, and there's many different ways to do it.
Great. Sugata, thank you so much for your presentation.
This is Raven Pack.